Okay, good afternoon. Let's continue on with our topic of discussion. Today I have a few show and tell items. These are actual silicon wafers from production facilities. This one, for both of them, actually, you can see microchips on there. The reason they are called chips is because they are cut out as small pieces of a round silicon wafer. You can see those small squares and rectangles, right? Shiny ones, almost processed. This one is reddish because it still has photoresist on it. So do not open the case and touch it unless you want your skin to peel off. Do pass out silicon wafers that you can actually touch. I was just kidding about the peeling off, but there is still chemical on it, so we don't want to touch it. Chances are nothing's going to happen, but still. Now these, again, are processed silicon wafers. I wasn't too careful with one of them, and so they're very brittle. You could drop in from an inch above, and it'll break. So let me not do that. And they have sharp edges and corners, so you might want to be careful about that too. So these are what we know as 8-inch silicon wafers. They are characterized by the diameter. Okay, diameter. So typical academic institutions have 4-inch silicon wafers and 4-inch machines and equipment. For us to work on them. And then this was Cal Poly. Okay. And let's see. Oh yeah, there you go. So these are oh, 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 oh. These smaller ones are the ones made by students like you from a few years ago. All right. So the big one, the glass plate is a mask that we use. And you can see Cal Poly Microfabrication Lab. And then this is made by students. That's the class we offer at Cal Poly once a year in the winter quarter. BMed 435, cross-listed as EE 473. So every week, students come into the lab. Well, in the theory class, they learn about, in the lecture class, they learn about the theory of fabrication. In the lab class, they come into the lab clean room every single week, and we build a process. We perform a process. Didn't need the alarm today because the Zoom didn't turn on, so it's good. All right. As I was saying, students come in every single week. We do a process every single week. And then at the end of the quarter, we hope to get diodes and resistors. Nothing fancy, but still, it's great that we have a clean room on campus. So if that's something that interests you, then you might want to keep that in the back of your mind. Let's see. This year, Dr. Hawkins or Ben Hawkins, he used to permit students. So he usually would teach the lecture class, and then Ben, Hans, and I would each teach one lab section each. So the lecture class, Ben would permit students to take it if you had completed 306 or were in the process of completing 306. But this year, I think he's on sabbatical. I'm not sure. Haven't seen him around. So someone else is teaching the class. I believe Dr. Rich Savage. He is actually the one who had set up the clean room many years ago at Cal Poly. So I don't know the story, but he's maybe retired and he's now back again as a faculty emeritus, perhaps. I don't know. But he is the one who's going to teach it. So his name is Dr. Savage, Richard Savage. Okay. So if that interests you, you might want to reach out to him. Okay, let's go to our notebook. and continue from there. Detour, not quite a detour. All right, 306. Chapter one was done. Chapter two. All right, band gap energy. So we stopped here. We're talking about the energy band structure and how the electrons that orbit the atom or the nucleus occupy certain bands, and these bands have energy, and these energy levels are quantized. So they are fixed. They are discrete levels of energy. They are not just random. So anyone have any questions before we move on? Okay. Once you're done with all the show and tell devices, you can please pass it to the front row and I'll collect it from there. Okay, so broad classification of materials is insulator, conductor, and semiconductor. Conductors always have electrons available for conduction. There's no gap between the conduction and the valence energy levels. In insulator, the gap between the conduction and the valence band is too large to be overcome. And because of that, there are no electrons available for conduction in ideal insulators. And in semiconductors, there is a gap. There is no overlap. There is a gap, but the gap can be overcome by external means. Hence, that is what makes them a semiconductor. So the first thing is that they should have 4 electrons in their outermost orbit. And the second is that the energy band gap must be such that it can be overcome. And that's what makes them semiconductors. So silicon, germanium, and carbon, they're all from column 4 of the periodic table. They all have 4 electrons in their outermost orbit. However, carbon, the energy band gap is quite large, greater than 5.47. Sorry, not greater. It is 5.47, so far greater than 5. And that kind of band gap cannot be overcome. And hence, it is not a semiconductor. All right. So how does it all work? Okay. For that, let's look at the silicon lattice structure. So this is an illustration, like a 2D illustration of what a silicon lattice structure looks like. Each one of these circles that we see here is a silicon atom. Each atom shares 1 electron with 4 neighboring silicon atoms, thus creating a stable outermost valence shell. So you have 8 electrons for a stable atomic structure. And so if you share 1 atom with 4, if you share 1 electron with 4 neighboring atoms, you now have 8. And so does every other silicon atom in that structure. Okay. So in this 8, these bonds that form between these atoms is known as a covalent bond. These bonds are strong, not easily broken. Okay. Now, everybody is familiar with the temperature scales: Fahrenheit, Celsius, Kelvin. And you'll convert from Fahrenheit to Celsius and Celsius to Fahrenheit without using a calculator. Anyway, that's not what I'm talking about. We're talking about the Kelvin scale. In Kelvin scale, 0 degrees Celsius is minus 200, 0 degrees Celsius is 273 Kelvin, 273 Kelvin. So if we go down the scale, we reach a point which is at minus 273 degrees C. Or that point is known as absolute zero. Okay, absolute zero. Absolute zero is the place where nothing exists in a sense. There is no thermal energy whatsoever. So we'll begin our explanation, our journey. Let's say the silicon lattice, which has atoms, is at absolute zero. So we begin there. 0. Zero Kelvin or minus 273 degrees C. Okay. Average room temperature is typically taken as 300 Kelvin, which is equal to 27 degrees C, which is how much in Fahrenheit? 27 times 2, 54, plus 32, about 86. But it's not quite 86, about 85, 86-ish. Okay, approximately, I would just say approximately. This is without performing any calculations. 86 Fahrenheit, which is not quite room temperature. I mean, 86 degrees would be hot for me. Oh, by the way, there was a comment, student comment about adjusting the heat in this place. There's no control. There's absolutely no control. That temperature is set at 50 degrees. So there's no control that's going in there. Well, facilities has tried. You should come see my office space. Facilities has spent countless hours inside our office space trying to like connect the thermometer in the, not the thermometer, the thermostat in there to the radiator that we have on the wall. Nothing doing. Once the central facilities boiler turns on, they have hot water coming in through these pipes, and it's just blowing heat. Even on 80-degree days, it's just heat coming out. As soon as we flip on the switch in my office, it's heat coming out. So some rooms in this building have chilled water pipes. They have active cooling. So this room only has hot water. And that's nothing, it's up to facilities. So no one else can control that. Anyway, coming back to our topic. So it's absolute zero, and it's absolute zero. It means it's so cold. It's so cold. If I was the atom, if I was the electron, I can't do anything. I'm frozen in place. I can't move left. I can't move right. I can't move up, can't move down, can't do anything. There's absolutely no energy to do anything. It is like a cold winter morning. You're snug and warm inside a blanket, and you don't want to get up for an 8 o'clock class. It's like that. You don't want to go anywhere. So it's absolute zero. Everything is frozen in place. There is no energy whatsoever. All electrons are occupying their spot. There is no movement whatsoever. Now let's say the temperature rises a little bit. From 0 Kelvin, you now go to 1, 2, 3, 4, 10, 20, 50 Kelvin. Now there's a little bit of heat. It is still freaking cold, but we say in technical terms, there is a little bit of thermal energy. As the temperature rises towards 0 degrees C, there is now, compared to absolute zero, there is now a little bit more thermal energy that is available. So at 0 degrees C, it is still frozen. Technically, water is still frozen, but there is a bit of thermal energy, and that allows few electrons to acquire that energy and to move out of their spot. If we compare that to room temperature, now we have come up 300 degrees. Okay, at room temperature, we're now up 300 degrees. So now you have sufficient thermal energy that a whole bunch of electrons have acquired thermal energy to move out of their spot. When they move out of their spot, they are carrying their negative charge with them. They are now free and available to conduct. Again, compared to absolute zero, at absolute zero, there is no movement whatsoever. But at room temperature, it has acquired sufficient thermal energy that some electrons, not a whole lot compared to the structure, but some electrons have acquired sufficient energy to move out of their spot, and they're now free for movement. What happens when electrons move? They carry their charge with them. They carry their negative charge with them. Charges, rate of flow of charge is electric current, and energy is also transferred. And that's the basic premise of electricity. When electrons are free to move, we say that they are carrying current, right? Because energy is being transferred. All right, let's take a short pause. Let me know if you have any questions. So far, so good. Oh, you got, yeah. So the question being asked is if we have a pure wire and we apply a voltage across it, and would we have and there's no heat, would you have conduction taking place? That's a very good question. My answer would be no, but I want to say I'm not sure. My best guess is that nothing should happen at that point. Yeah. But if it's a wire, it's made out of metal, so it always have electrons. But I don't know. Okay. All right. So let's say now we're at room temperature. There are certain electrons in this lattice structure that are moving, right? If they are moving, where are they going? They're free to move around within the lattice structure. They may be a part of another atom, or may they become a part of another atom if it has space. Because if one electron moves out, it's going to leave an empty spot, right? So it could move into another spot, forming another covalent bond, or it could just be free to move around within the lattice structure. The key thing that happens is this. You have an electron. Once an electron moves out of its spot like this, what is left behind? What is left behind is an empty spot. And that empty spot is literally known or called as a hole, H-O-L-E, hole. So it's an empty spot that is created when an electron moves out of its spot. And in physics and in electrical engineering, it helps to treat this hole as a particle in its own right. And just as electrons have negative charge, the holes are associated with that corresponding atom, which has an extra proton, which means it now has one extra positive charge. So for every negatively charged electron that moves out of its spot, it leaves behind a positively charged hole. And in all of solid state physics, we treat this hole as a particle in its own right with a positive charge. So we have electrons. I have negative charge. And then we have holes, which are treated to have, or which are said to have, positive charge. Okay. Right. So far, so good. The key difference between the electrons and the holes is that the electron is free to move anywhere. Free to move anywhere, right? But a hole will always move in specific spots. By its very nature, by its very definition, a hole is always in the place where the electron was. So it can only move into certain specific spots. As the electron moves one way, the hole moves another way. So let's say an electron moves out and it moves out and it creates an empty spot. When you create that empty spot, there are other electrons that have acquired energy and they can move into this spot and they thus create an opening when it moves out. So it's a cascading effect, so to speak. It's a cascading effect. So if you have an electron that jumps over one spot, it leaves behind a hole. And so if electrons are moving to the left, we say that holes are moving the opposite direction or to the right. Okay. And you perhaps have come across this before. Electrons are flowing one way, holes are flowing the other way, and we take that as the flow of current. All right, how much time? We've got 11 minutes left. So far, so good. Okay. For every electron that leaves its spot, it creates a hole. So the electron and that hole is known as an electron-hole pair. And that process is known as generation. So it's known as an electron-hole pair, and the process is known as generation. Generation. So when an electron acquires sufficient energy to break its bond and move out of its spot, it is generating a free electron, and free in this term, in this sense, is free to conduct, free to move. It's free to conduct electricity. That's what it means. So it generates a free electron, and we say it's called a generation of an electron-hole pair. Yes. When an electron moves, so question being asked is, how does a hole form? The hole forms when an electron leaves its spot. So that empty spot is simply labeled as hole, as a hole. Yeah. Yes. Yes. So the question being asked is, how does it leave its spot? It acquires sufficient thermal energy, and that energy allows it to jump up levels and move out of its spot. Okay. Yes. We are jumping ahead, but yes. So question was about doping, and that comes up in just in few slides after that. Yeah. Yeah. Okay. So we spoke about how electrons can move out of their spot, but I also said electrons can move into another empty spot, right? So if you have hundreds of thousands of electrons that are free and moving around, you have correspondingly hundreds of thousands of holes. And so there are some electrons that will jump into that spot and release energy. When an electron jumps into an empty spot, we say that it is recombining with a hole, and that process is known as a recombination. So the process of Electron jumping out is known as generation. An electron combining with a hole electron moves into a spot is known as recombination. Recombination. Okay. And here's the key thing. Remember, I said in order for an electron to move out, it needs to acquire energy. So it acquires energy and it moves out. So what happens when it falls back into a spot? Releases energy. And the released energy can be in the form of heat or light. Okay, heat or light. Okay. So far, this generation of electron hole pairs is solely due to thermal energy and not due to any other external source or applied source. Only due to the surrounding environment, meaning I take a piece of silicon and it's sitting at room temperature. Let's say it's 80 degrees in here, and there are free electrons that are available for conduction, but they are not in sufficiently large numbers so as to behave like a metal. Hence the name semiconductor. Okay, so it's not quite pure insulator and it's not quite a pure conductor, but a piece of silicon like this sitting at room temperature has free electrons. So that begs the question. We have this process just sitting here at room temperature is generating electrons, and then those electrons are generated, they are jumping back into spots. So some are being generated, some are jumping into spot. So what is this cycle? Right? We have generation and recombination, generation, recombination, generation, recombination. Well, in all semiconductors, it has been observed that the process is stable, meaning at any given temperature, the rate of generation and the rate of recombination always balances out. And that is known as thermal equilibrium or just equilibrium. Okay. So the rate of generation and the rate of recombination is always balanced. And this is defined as thermal equilibrium or just equilibrium, I would say. Let's see if I can spell this correctly. I think I got it, equilibrium. Also, all the electrons and all the electron hole pairs that are generated are solely due to thermal energy. So they are intrinsic or inherent or inside the material itself. Hence, these semiconductors are known as intrinsic semiconductors. So it's something that is inherent or inside the material solely due to thermal effects. That's all. And so there are researchers and physicists and scientists who have done research in this area, and they came up with mathematical equations that describe the intrinsic carrier density. And that is referred to as Ni. Ni stands for the number of intrinsic free carriers that are generated. Okay. In general, Ni refers to the intrinsic carrier density. So Ni stands for intrinsic carrier density. Okay. Sorry, intrinsic carrier number, not density, just intrinsic carrier numbers. So it's just the number of electrons that are generated. And then N is generically, so here's where it gets confusing. So I'm letting you know right up front, even before we go into other mathematical equations and notations. Ni refers to both electrons as well as holes. Okay, but N by itself simply refers to electrons. And then P is used for holes. So Ni, if you have a subscript, then it's the intrinsic carrier number. And N is the number of electrons, and P is the number of holes. Okay, let me write it out better way. So number of electrons and number of holes. A few seconds left. In an intrinsic semiconductor, because a hole is generated for every electron, the number of holes is always equal to the number of electrons. N is always equal to P in an intrinsic semiconductor. Okay. And N times P gives you Ni square. Okay. All right, we'll end class here today. I'll pick up here again on Wednesday, and we'll focus more on this equation. There's some reading material in the book, so please get started on that on chapter 2. There are some solved examples in the book too, so please review that, and we'll talk about it in next class.